In this video, we're going to work example problems where we're given a series and we want to determine if it's convergent or divergent. Now, mainly for these problems, we're focusing on the integral test for convergence, but it could be the case that for some of these problems, we'll see that the integral test can't be applied to that particular series. And so we'll have to use another method to determine convergence or divergence. And at this point in this chapter, we only know of one other method to determine convergence or divergence. This is all assuming that we can't find the S sub n for the series. If we can find the S sub n, well, then just take the limit as n goes to infinity of the S sub n formula. If you can find the S sub n, you don't need any tests for convergence or divergence. You just take the limit of the S sub n as n goes to infinity. If it diverges, you'll see how it diverges. If it converges, you'll get the answer to what it converges to. That's the series. If you can't get the S sub n, then you still want to analyze if the series is convergent or divergent. And we're going to focus on the integral test for convergence or divergence in this video. But what we've also learned about in the test for divergence. So we also are aware of the fact that every single series has an A sub n associated with it, right? That's what's being summed, the A sub n. We know that we can take the limit of that sequence, of that A sub n sequence, and if it doesn't converge to zero, if it diverges or it converges to something other than zero, then we know that the series is divergent. And so we can use that fact to determine if the series we're presented with is divergent. Now, if we find that A sub n converges to zero, then we haven't learned anything. Okay, so we have that in our toolbox as well. All right. So looking at this series, we want to determine, is it convergent or divergent? And again, we're mainly focusing on the integral test with these problems. And so for the integral test, you first need to analyze the series, in particular the sequence formula, to see if that series is applicable for the integral test. The integral test can't be applied to just any series. And what you do is you take the A sub n for the sequence. So this is and we can see this A sub n, actually the limit of this A sub n is 0, which doesn't, if we saw that if we saw that the limit of this A sub n was equal to something other than 0 or divergent, then we would be done. We would just say that this is divergent. But we see that the limit of this A sub n is actually 0, so it still might be divergent. We don't know. But we have to do further tests to figure it out. Okay, so what we do is we look at the sequence formula in the series, and we replace the n with x. And with that, to apply the integral test, this function over the range of the series, so this would be from 1 to infinity, needs to be continuous, positive, and decreasing. Okay, and so we see that this is continuous for, at 0 it's not, but from 1 to infinity it is. It's always positive from 1 to infinity, and it's decreasing. Every single value as you go is less than the previous value. Now, remember, technically, there is a caveat to this in that the decreasing constraint, it doesn't have to be decreasing from the entire range, as long as there's at least you can find one number, n is equal to 10 or x is equal to whatever, 10 or 20, where from that point on, it's all the way out to infinity, it's decreasing. Then you can still apply the integral test. So like you could think about it like you would take this derivative and solve for where the derivative is less than 0. If it's always negative for any x, it doesn't matter what it is, x starting at x is equal to 5 or 10 or whatever, then that's applicable here. Okay, so with that, the integral test can be applied to this series, and all you do is you just take the improper integral from the start point of the series to infinity of the function of x, what you replaced n with x. And it's just about seeing if this converges or diverges. You don't really care if it converges what the value is. It's just if this converges, then this converges. If this diverges, then this diverges. If it converges and you get a value, you're not really concerned with that value for the integral test. Okay, now we don't need to go through this evaluation because this is a case that we already derived in the book, in the textbook section. This is a p-series. Okay, a p-series is of this form, and that's the exact form we have. If p is greater than 1, it's convergent. If p is less than or equal to 1, it's divergent. 3 is greater than 1. So this is convergent. And that's it. We're done. We're just trying to answer the question, is this convergent or divergent? That's it. Remember, because now that we know that this is convergent, if we couldn't get the S sub n formula, the explicit S sub n formula, we could do an estimate for this sum. So this is just about determining if the series is convergent or divergent. That's it. Okay, so we could take a glance and just see, is the sequence formula, the limit of it, is that divergent or doesn't converge to 0? That's a quick check if you can just take a look. And so here, this, as n approaches infinity, this goes to 0, so that doesn't tell us anything. All right, so now we need to look at the integral test. That's the only other tool we have to analyze for convergence or divergence of a series. So we replace the n with x, and then we look and see for x is equal to 1 to infinity, is this continuous? Well, all right, when x is equal to 1/5, this is equal to 0. The denominator is equal to 0. When x is greater than 1/5, this is positive. 2 is positive. So this is always positive because we're starting at 1. We're starting at greater than 1/5. It's always continuous, right? The only potential discontinuity is when you're dividing by 0. And then is it decreasing? Well, yeah, because as x gets larger and larger, you're always getting a bigger and bigger denominator. So we can use the integral test here. And so all you do is once you see that this is applicable for the integral test, you take this f of x and you go from the range of the series, the improper integral of that function of x, and that's it. And if this is convergent, then the series converges. If this is divergent, then the series diverges. That's it. Okay, so how do we take an improper integral? Well, go review the improper integral section if you need. We say this is the limit as t approaches infinity of 1 to t. Right? So now let's solve this integral. We want to make the substitution. That u is equal to 5x minus 1. So therefore 1/5 du is equal to dx. So we've got when x is equal to 1, u is equal to 4. When x is equal to t, u is equal to 5t minus 1. Okay, we can take out this 1/5, even in front of the limit. And we've got 2. We can take out the 2 as well. And we've got 1 over u du. So this is 2/5, the limit as t approaches infinity of, so this is natural log of the absolute value of u evaluated from 4 So we've got natural log of minus natural log of 4 is 2 natural log of 2. Okay, so as t approaches infinity, this just goes to infinity. Infinity minus 2 natural log of 2 is infinity. So this is equal to infinity, which means this integral diverges. So this series is divergent. Okay, let's just take a look at the sequence first. And if we divide the numerator and denominator by n squared, now the limit as n approaches infinity of this goes to 0, this goes to 0, so this goes to 0. So that doesn't tell us anything about the series being divergent. So, okay, if we replace the n with x, then from 1 to infinity, this is always a positive function. It's always continuous. We can never divide by 0. And then it's decreasing. The denominator will always get bigger and bigger and bigger relative to the numerator for every single x. Okay, so the integral test from 1 to infinity this is equal to okay, so what is this? Okay, if u is equal to x squared plus 1, then 1/2 du is x dx. When x is equal to 1, u is equal to 2. When x is equal to t, u is equal to t squared plus 1. Take out the 1/2. You've got 1 over u du. Okay, so we've got, so we don't need the absolute value because we're going from 1 to infinity. So natural log of t squared plus 1 minus natural log of 2. Okay, so we've got 1/2 the limit as t approaches infinity of natural log of t squared plus 1. So this goes to infinity. That means infinity minus natural log of 2. So this is equal to infinity. So this is divergent. Okay, this is a p series, right? 1 over n to the p. P is any number. If p is greater than 1, the square root of 2 is greater than 1. So this is convergent. Okay, here they don't give us the a sub n, but we could determine it using these initial terms. So let's get the a sub n. So it's going to be 1 over something. So this is 2 cubed. This is 3 cubed. This is 4 cubed. So there we go. We've got 1 over, and if we're starting at the first term is n is equal to 1, so we want to say, so it would be n cubed, right? This is 2 cubed. This is the second term, 3 cubed. Okay, so if we put this into the summation, we've got, okay, we just had this a few problems ago. This is a p series with p is greater than 1. Okay, so we've got 1 in the numerator, and then, so let's see, 3 plus 4 is 7, 7 plus 4 is 11, 11 plus 4 is 15, so a arithmetic sequence in the denominator. And okay, so the arithmetic sequence formula is you've got the first term plus the common difference times n minus 1. If we're starting at 1, 3 plus 4n minus 4 4n minus 1. Okay, so we've got, writing this as a sum, okay, can we use the integral test? Let's replace n with x. All right, this is for starting at 1. 4 minus 1 is 3. So this is always positive from 1 to infinity. This is always continuous from 1 to infinity. And it's always decreasing as well. You always the denominator is always gets bigger and bigger and bigger as x increases. So we can apply the integral test. We go from 1, we start 1 here to infinity. So this is equal to the limit okay, so this integral we say u is 4x minus 1, so 1/4 du is dx. Okay, when x is equal to 1, u is equal to 3. When x is equal to t, u is equal to 4t minus 1. So we've got 1/4. Natural log, we can take away the absolute value because we're going from 1 to infinity. It's always positive. Minus. Okay, so we've got 1/4 the limit okay, this goes to infinity. Infinity minus natural log of 3 is infinity times 1/4 is infinity. So this is divergent. Okay, if we replace n with x, all right, is this continuous from x is equal to 1 to infinity? Yes. Is it positive? Yes. Is it decreasing? So just glancing at this, it seems to me that this is decreasing. Just, x squared is going to increase faster than square root of x. But we can take the derivative just to see. So derivative of the top times the bottom. So x squared over 2 root x. Minus derivative of the bottom times the top all over the bottom squared. So x squared over x to the 1/2, which is 4 over 2 minus 1 over 2, x to the 3/2 minus 2 times x to the first, 2x times root x, that's 2x to the 3/2, we'll do this, plus 8x. All right, so this is always positive, and we can see that the numerator is always going to be negative. You've got the x to the 3/2, but this is multiplied by 2, and you're adding an 8x, and x is always positive. So this is always going to be negative. So it's a decreasing function, but it didn't even have to always be negative from 1 to infinity, as long as it's always negative for starting at some x value. So when you look at it from that perspective, it's not like we need to check to make sure that it's negative when going from x is equal to 1 to 2 or something like that. We could see for sure, it looks like it's negative even starting at x is equal to 1, but it's definitely negative once you get past 1 for sure. So, okay. So we can apply the integral test. we want to evaluate the improper integral. So the limit as t approaches infinity okay, so this integral, we can rationalize this. Let's say that u is equal to root x. So u squared is equal to x. Therefore, we've got 2u du is equal to dx. All right, so we've got when x is equal to 1, u is equal to 1. When x is equal to t, u is equal to root t. Then we've got u plus 4 over x to the 4th is u to the 8th. Okay, then dx is 2u du. So we've got okay, so this is we could take out the 4. Okay. All right, so we've got, so minus 6 plus 1 is minus 5. U to the minus 5 over minus 5. So that's minus 2 over 5. Okay. And now we're going to have u to the minus 6 over minus 6. So minus 8 over 6 is going to be, so minus 4 over 3. Then so 1 over root t to the 5th. So we can just say t to the minus 5 halves, then minus 1, minus 4 thirds, 1 over, so that's going to be t to the minus 6 halves, so t to the minus 3 minus 1. So minus 2/5 t to the minus 5 halves plus 2/5 minus 4 thirds t to the minus 3 plus 4 thirds. Okay, so minus 2 over 5t to the 5 halves minus 4 over 3t cubed plus 2/5 plus 4 thirds is what? That's 6/15 plus 20/15. That's 26/15. All right, so we've got the limit as t approaches infinity of okay, as t goes to infinity, this goes to 0, this goes to 0, this limit goes to 26 over 15. So this limit converges. So that means that this series converges. But this limit value doesn't really mean anything to us. Okay, so just looking at the a sub n, we see that the limit of the a sub n is 0, so that doesn't tell us anything. Now if we look at the f of x, this is positive, decreasing, and continuous from n is equal to 1 to infinity for sure. So integral test, 1 to infinity. Does this integral converge or diverge? Okay, so let's look at this integral. So u is x squared plus 4, therefore 1/2 du. Well, okay. Okay, so we can't make a substitution here, but if you remember from the partial fraction decomposition section, when we've got this form right here, this 1 over variable squared plus constant with the leading coefficient on the variable 1, this is going to be, so this integral. Again, we did this a bunch of times in the partial fraction, the integration of partial fractions section, like almost so a lot of problems. We had this form, and this is equal to, no, it's 1 over a arc tangent. That's what that's equal to. So in this case, a is equal to 2. Square root of 4 is 2. So we've got, this is 1 over 2 arc tangent of x over 2 like that. So take out the 1/2, and we've got arc tangent of t over 2 minus arc tangent of 1/2. Okay, arc tangent of 1/2 is not anything clean, but it doesn't really matter. So, okay, we've got, yeah, let's just put this here. So we've got, we can take out the 1/2. We've got the limit as t approaches infinity of arc tangent t divided by 2 minus arc tangent 1/2. Okay, as t approaches infinity, I believe that's going to converge, arc tangent. As t approaches infinity, arc tangent of t divided by 2 is pi over 2. So we've got 1/2 pi over 2 minus, and there you go, pi over 4 minus, I mean, this, the value doesn't matter. We see it converges. So it this integral is convergent, so that means this series is convergent. Okay, we'll continue with more problems in the next video.